Shall we start? Everyone's here. Okay, so welcome to the plastics value chain parallel session of the TREASoURcE project. So we will start with the plastics key value chain introduction. I will introduce you very briefly, and then Chan will be presenting the challenges and policy recommendations for you. Okay, maybe my voice comes better now. And then Jan will be introducing you more specifically about the plastics value chain stakeholder engagement. Then we will be moving on to the sustainability assessment narrated by Alex from Green Delta. And Stefan will be mostly presenting the optimizing mixed plastic feedstock for high efficiency recycling. I will also help him a bit. And then we will have a coffee break for 15 minutes. Then Christian and Juha from VTT will be explaining you more insights about the chemical recycling for closing the loop of plastic waste. Then we will have a panel discussion. Juha will be the moderator again from VTT. Then we will have a short coffee break again, and then go upstairs again to the plenary room. So, plastics key value chain introduction. So Christian already touched these points in the morning, but I would also like to give a little bit of a brief information. So our objectives are efficient plastic collection, sorting, and pre-treatment, where there are currently unused or untreated mixed plastic waste streams are challenging currently. So not really well recycled streams, but we are targeting on the difficult to recycle streams. In the next slides, I can explain you better on this one. Actually, this one. So we have chosen three different type of plastic wastes. One is agricultural, the other one is municipal, and the last one is industrial. We start from the collection stage, and then we continue with the pre-treatment and sorting for the feedstock preparation. And we utilized a complementary approach here for mechanical and chemical recycling. The project consists mainly of the chemical recycling activities, but we didn't want to rule out mechanical recycling here, as there are many complementary values that mechanical recycling can also bring. However, there is also a possibility to have mechanical recycling itself only. So here, for the chemical recycling, we have two routes for pyrolysis, but thermal pyrolysis and catalytic pyrolysis. And we also upgraded the pyrolysis oil with the hydrothermal treatment. As the complementary approach for mechanical recycling, we use it as a pre-treatment method with an extruder called Modix. We will go through the details later on for Modix and Varex, and then also chemical recycling activities. What we targeted here, either to retain or upgrade the mechanical recyclable plastic waste streams to have better properties or retain properties, or we targeted to have new polyolefin plastics, not in this project, but we targeted to have naphtha as the product, or BTX for new building blocks in chemical industry, new chemicals, naphtha as new petrochemical source, BTX as added value chemicals in the future. And with this, we believe that we are adding value to circular economy by reducing the emissions caused by oil and gas industry. These are general terms, but still good to notice. And technology development for recycling technologies, new consistent and reliable plastics recycled feedstock, and mitigate geopolitical risks for supply chain. I think it was well touched by one of the presenters in the morning, Stefan. So now I can give my words to Chan for the plastics regulatory challenges and policy recommendations. Thank you.
Okay, hello everybody. So my name is Chen. I'm a research scientist at VTT. So in the morning session, we have raising hands and agrees as policy is one of the most critical element to enhance the circular economy. So that's why we also study it here within our project. So here I will share with you some results from our plastic regulatory mapping and the policy recommendation that we formulated. Okay, so first of all, I will tell you how we implement our regulation mapping. So first, we did a lot of that research to map the European policy, and through that, we identify the key driver and barrier from the policy and the regulation landscape. When we get the first insight, we create a lot of workshop and stakeholder engagement activity so that we can ask the stakeholder like how is the insight here? Is this applied to your practice? And is it relevant? Is it validated? And after we receive the insight in combination with the data research, we formulate the policy recommendation. Okay, so here is the five of the key things that we withdraw from our study. You can see the five here is the five main theme. It can be that related to the key driver and barrier for the plastic regulation. The first theme is related to the plastic waste collection, sorting, and other logistic activity. The second theme is about the feasibility of the recycled content requirement and also the bio-based plastic alternative to the fossil fuel one. The third theme is about the plastic recyclability, and it's also including the design for recycling and some advanced solution like chemical recycling. The fourth theme is about the economic profitability of the circular plastic solution. So in order to for the plastic solution to be scaled up, so of course it needs to be somehow profitable. So from this study, we also produce the policy brief. Its name is enabling the complementary of mechanical and chemical recycling in plastic recycling. Okay, so now we go to the first theme about the plastic waste collection, sorting, and logistic. Oh, sorry, I moved it a lot. You can see that I put on the left side is the key driver and barrier, and on the right side is some of our policy recommendation. So the first thing is about enhancing the waste collection and separation. We have some suggestion for the, we should have some policy incentive and financial to enhance it. Some example here is through the emission trading system. So if you are like taxing the waste incineration, so it will reduce the waste coming to the incineration and increasing the percentage of the plastics that will go to the recycling more than incineration. And as a financial inducement that we can do is the extended producer responsibility. We mention it a lot, like we can get the finance from here to handle the waste collection and recycling. Uh, yeah, and the last recommendation is about forming more plastic and waste criteria. So more plastic cannot be end up as waste, but it can end up as a feedstock for the recycling process. Uh, yeah, another driver issue, the driver for the plastic policy that we think could be beneficial is the eco-modulation of plastic recyclability by design. So eco-modulation is that the recycling fee for this product will be determined by the recyclability of the product. So you have more environmental friendly product, you pay less. But if your product like is not so environmental friendly, it cannot be recycled, you should be taxed more. So it can enhance the desire for recycling and encourage the designers, the producer to produce more environmental friendly product from the design phase. The two topic is the feasibility of the recycled content requirement. So the first theme here is is a is a barrier. So we identify that there is a gap between the recycled content requirement and the current recycled quality management right now. It means that like there's some of the regulation right now that just the recycle content requirement, but also the recycled are managed like is managed very strictly. So you have the recycle content requirement high, but also the restriction is also high. So there's a suggestion here that we somehow could update the regulation. For example, you can see here the plastic recycling regulation. So we should facilitate more alternative recycling option, like more, it should include more mechanical and chemical recycling solution that can meet the recycled quality and safety. So we can do more product in the context sensitive packaging, so we can bridge the gap between the recycled content requirement and recycled quality management. Yeah, the second theme here is about the lack of regulatory framework for the bio-based material alternative to plastic. In order to adapt more bio-based material, we should establish more regulation framework, should be tailored to the bio-based polymer, to covering more of its production, its use, its quality control, and the enterprise management. Yeah, and also some standard technical guidelines. It can facilitate a lot of integration of bio-based material to the plastic circular economy. The third theme is about the plastic recyclability, also includes the design for recycling. Yeah, the first thing is the lack of standard for plastic recycling practice. I think the specific thing we mentioned here is that we're lacking the standardization for the chemical recycling, and also its product like the pyrolysis oil. So yeah, we of course need to establish more standard for it to make the also make the product more, make the process more mainstream, and also make the product more mainstream also on the market. And the other barrier is about the complexity of the product design and the process design. If the product are designed in multi-layer and use not so environmental friendly material, it will be, and or maybe some adhesive labeling inks, it can make the recycling process very difficult. So that's why we need to enact more eco-design and also improve the material traceability. So we know the composition of the plastic waste feedstock. So from that, we can further improve the safety and also the quality of the recycled plastic. Yeah, and more experiment in research, development, and innovation are needed. So that's like more advanced mechanical recycling can process more problematic waste fraction, and it should be complemented by the chemical recycling. It is also the things that we will write the policy brief about complementing the mechanical one and chemical recycling one. Yeah, but before we come to that policy brief, there is the last themes that we identify. It's about the consumer acceptance and the cost effective of the circular solution. Yeah, so for the more cost effective solution, we can implement more sanction for using the raw material, the virgin fossil-based solution, following the polluter-based principle. We can also implement more consumer protection and develop more sustainability labeling and certification scheme. So we can ensure the transparency of the product so the consumer know where it's from, where it's produced, and how to recycle such product. We can also invest in the consumer education program, so to empower the individual about the information so that they can make the decision. And public procurement scheme, I also mention very frequently, but it's very helpful to create the demand for the secondary plastic market. Yeah, so this is the policy brief that we produce in our project. I already mentioned you about, it's about like we should complement the mechanical recycling and chemical recycling process. The mechanical recycling is quite well established and energy efficient now. Yeah, because it can it can be the cornerstone of the circular plastic solution. But when it comes to more problematic plastic feedstock, like the multi-layer, the film plastic, so we need more developed solution to handle that kind of problematic. So the chemical recycling can play the complementary role here. Yeah, so it can enable the use of the kind of the problematic polymer and bring it back to the circularity. Yeah, but as I already mentioned, chemical recycling is not like officially approved as a recycling method right now. So that's why we're forming some of the policy recommendation here. Yeah, the first thing I already mentioned, the development of end-of-waste criteria, also strengthen the waste separation and sorting so we have good quality of the feedstock. Recognize chemical recycling under the European regulatory framework. And also the last thing is expanding the scope of the food contact regulation. So it can enable more innovative recycling solution like the chemical recycling. So it can be recognized and the product and also the process can be mainstream. Yeah, it can open the market and also open the investment for the recycling technology. Yeah, so finally, I can say that all of our result from the regulation study is documented in one of our deliverable. It's already published on our website. Yeah, so if you wanted to know more about the whole result, it's not only for the plastic, but also for the bio-based and also for the battery regulation as well. All of this regulation study are combined into this D1.3 deliverable. And the plastic policy brief is coming very soon on our website. Yeah, if you follow us on social media, you probably will get the news about it when it published. Okay, so that is all. Thank you a lot. If you have any question, yeah, ready for answer. Okay, so then thank you very much for listening. Yeah.
It on? Yeah. So hello everyone. Jan Bakke, project manager for County Authority of Østfold. I'm going to talk about C-Smart procurement recipes for circular plastic, which is a topic we've been working on a lot in the TREASoURcE project, especially for public procurement. So, as been mentioned before, C-Smart procurement is a very important tool on the demand side to drive the markets both for reusable and recycled plastics. And these are some of the, and it's based on the waste hierarchy, which you see to the right, where you start with the most circular solutions first, which is also about preventing waste from happening and reducing the amount of material, and then you get to the recycling and you progressively go downwards. But some of the main elements are for public procurers, when we give them guidance material, is that they should always do market inquiries with the suppliers, either with meetings or directly with the suppliers to assess circular readiness for the solutions in the market, and then base their requirements on that. And if at least 3 or all suppliers confirm that they can deliver the requested circular qualities for the products or the services, then you should set it as a minimum requirement. And a minimum requirement is something all the ones participating in the tender have to comply with for their tender to be accepted. If fewer than 3 respond yes, or they give inconclusive responses, consider using an award criterion where they are awarded. So we've made checklists for public procurers in all stages of the procurement process for both packaging, circular criteria for goods, for textiles, for construction waste, and waste bags and containers. And here you see an example of some of the main sort of structure of the checklist in when it comes to circular criteria for goods. First, you talk about how we can eliminate the need for new products. Do we have to make a procurement at all, or can we have a reusable ones? Secondly, you go to buying second-hand items. Then you buy product. You look at buying products as durable as possible and environmentally friendly as possible, looking at eco certifications, materials they're made from, like recycled plastic and recycled plastic content, and whether the products actually are materials are recyclable. Before you go to the last, how are they disposed? Can, for instance, the products be reused and repurposed in the same organization or in the supplier's market afterwards, so the products don't go out of use? And here's an example of how the checklists are structured. They're always divided into sort of into tables where you have market inquiry questions on the left-hand side and suggested follow-up actions based on the responses you get in the market inquiries on the right-hand side. For instance, you could say, is there a market for purchase of second-hand products, or can you offer products with recycled materials for this contract? Yes for all, yes for some. And if you get as much as 3 yes, then you can set a minimum requirement, and then the checklist also will offer standardized kinds of wordings you can copy directly into the tender, both for minimum requirements and sometimes also for the verification requirements. One of the main elements when we're trying to sort of scale up also public procurement for circular plastics is how to create market predictability for the suppliers and the ones who are participating in the tenders. And one of the important things is to use standardized requirements and evaluation criteria, which you use over and over again in the same type of procurements. So there's a predictability for the market operators of what kind of products or qualities are we looking for? What kind of standards will they be evaluated on? And also an important element, if it's possible, based on the market inquiry, avoid plastic materials which cannot be recycled. That's an important requirement. And also to require or award recycled plastic. And here you see an example of a requirements specification based on this, all plastics, which can be used directly in the tender. Does there have to be an opposition between costs or economic thrift and circular criteria? Not always. What we've seen from the best practices here is when you're applying circular requirements and criteria which reduce consumption or which prioritize the circular solutions, you can also combine lower costs with circular requirements. And in order to make this work, it's also necessary not only to have it in the contract itself, but you need to also have routines in your organization which prioritizes the circular choices and make them the sort of the default solutions for the people in the organizations who are going to order the product afterwards. So it's much easier and it's a standard that they use the circular solutions which the agreement offers. And also it's important to work with communication and cultural building within the organization, communicating why we do it, how much money have we saved, how much climate gas emissions reductions have we had, and a number of like share of recycled items in the contracts and those kind of things. So, and how do we then go from pilot cases to a more systematic approach? Then we need to work with procurement strategies. And in the procurement, we've made a list of wordings which can be used in procurement strategies where for different categories of procurement. And these lists, they contain smart, measurable objectives, which we need first, then a concrete action which can implement the set objective, then what kind of routine or recipe or criteria will we use to implement this kind of action, and reporting. How will we monitor sort of the performance of the practice in our organization afterwards? And together, by using this systematically in different categories of procurement in your organization and in your procurement strategy, you can make a much bigger impact, because it's not just a pilot case. It's something which is used as a standard routine in a lot of different tenders and also in different regions. So that was the main things I wanted to stress in this presentation. Thank you very much for your attention. You can find the checklist here on the publications on the TREASoURcE page, and also valuable examples for in the replication handbook of the project. Thank you.
Thank you very much, Jan, for this nice presentation. So now I would like to invite Alex from Green Delta for sustainability assessment.
Yes, thank you very much. For those who don't know me, I'm Alexander Koch from Green Delta. We are a sustainability consulting and software development company based in Berlin. And in the TREASoURcE project, we conducted the sustainability assessments for all the three key value chains. So today I'll be introducing you or showing you the sustainability assessment results for the case of circular plastics. So for the value chain we looked at in the project relating to plastics. Just briefly, goal and scope. So for the sustainability assessment, we wanted to assess the introduction of a chemical recycling plant in terms of its environmental impacts mainly, and kind of use those or present those results and to support decision making, especially for policymakers. The region where we conducted this assessment was chosen to be Gothenburg, Sweden. This was initially chosen together with our partners Polyfuels, or ex-partners Polyfuels. And we looked at different material flows, agricultural, industrial, municipal plastics, and chose basically the main polymers, HDPE, LPE, PP, and PET, to be assessed. The system boundaries, so we're looking at a chemical recycling plant and installing that chemical recycling plant at a specific or a certain capacity in the region, Gothenburg, Sweden, and looking at how this introduction or this construction results in a change of material flows, and linked to that in a change of environmental impact. We're looking at the two output streams and how they can replace certain primary or virgin materials on the market. but also looking at how now with an introduction of higher recycling capacities, we can avoid other ways of disposing, for example, or end-of-life strategies for those used plastics. Our method is a unique one or a novel one. So we did not only apply a classic life cycle assessment. This is the approach you usually use to conduct environmental impact assessments. But since in the TREASoURcE project, we're looking at systemic solutions and also regional solutions and engaging stakeholders, demonstrating certain solutions within regions, we kind of developed a new approach of doing sustainability assessments and introduced additionally to an LCA, a life cycle assessment, the approach of system dynamics to kind of include a wider scope of the system boundaries, not only looking at the product specific process steps, but also looking at the wider system in terms of the market or the context in which that specific technology is being introduced. And the combination of this, so combining system dynamics and LCA, we're using the software OpenLCA and open source LCA software, where we also developed a system dynamics feature now. We can basically conduct context-specific system dynamics sustainability assessments and kind of model different scenarios over time and see how the introduction of a technology leads to changes in material flows. So results. First of all, the LCA results. So we did an LCA study first. And here's just one comparison of HDPE granulates, so primary HDPE plastics compared with basically HDPE coming from a chemical recycling pathway. And we see that most categories, so these are the impact categories in the environmental footprint impact assessment method. And most impact categories, the chemical recycling route is better. So we can see that in the impact category climate change, it is better. In the impact category resource use, of course, it is better. But there are still some where you can see there is a higher impact in terms of the higher impacts for the chemical recycled HDPE. These results are mainly based on literature sources and secondary data. We used publicly available or available generic LCA databases, but also scientific literature to come up with these studies. And these will probably, these results, and these will probably still be updated once we get more data from our partners in the project. When you look at the hotspots, this is basically just the chemical recycling, chemical recycled HDPE, we see the main contribution is coming from, at least for some categories like climate change, is coming from the ethylene production and the polymerization, so almost 90%. Same goes for the resource use category. Almost 90% is actually coming from the ethylene production. So the actual chemical recycling part is not a very high contributor. When we look at the prospective results, so we are comparing here the virgin material on top mainly and the chemical recycled material. Over time, basically, we see that the chemical recycled part is better in terms of these two impact categories. And over time, you even have a decrease because the energy mix is improving in the region and is going from fossil to more renewable. And then coming to the system dynamics part, so this was really just the product level results. We basically then constructed a system dynamics model. It includes basically a core element, or core part, which is the material flows, and we're really looking at primary plastics being introduced to the market, then reaching end of life, and then we have different end of life flows. One being the circular flow, which then feeds again the plastic market. And for the circular part, we're also considering sorting rates, recycling capacities, additives that are required, and so on. And then we have the external environment, let's say, of the system, where we're looking at circularity indicators. Here we're seeing how does recycling capacities change over time. Then we have the market. How is the price development of plastics? How does this affect the demand and supply? Then we have context indicators. How is the consumer? How does the consumer behave? What are like how does technology develop over time? What are some government support strategies that are changing these flows here? And with that, we can really, and the LCA results, we can conduct a more wider sustainability assessment, including all the different elements of a relevant system. Here, just a brief, this is just an overview of the context indicators we looked at, and these are the scores for Gothenburg, Sweden. We looked at how well the infrastructure is in place for the specific technology, circular participation. These are really basically calculated scores based on real data. How well are consumers informed? And based on these scores, basically, we can model different scenarios and say, what if we increase now the consumer participation, for example? How does this affect basically these material flows that we're modeling here? Yeah. So then we modeled 4 scenarios, business as usual, what if nothing else changes, and we continue with mainly mechanical recycling and quite a lot of disposal of plastics. Then we have one scenario where we increase chemical recycling, one scenario where we improve or increase government support, one scenario where we have also consumer awareness being increased. So, and these are basically scenarios built on top of each other. And then we basically define certain scores for these, or certain parameters for these different scenarios, and ran the model. And this is some of the results we received. So we're looking at the 4 different polymers, especially the change in material flows for the business as usual scenario. And we see that, you know, the production of primary plastics continue as is, but we have an increase of mechanical recycling, especially in the business as usual scenario. And that's why this market is satisfied with that increase when this basically stays the same. There is an increase in demand for plastics over time. But then when we look at the different scenarios and how the material amounts change over time based on the different scenarios, we see that, okay, there's an increase in, down here, the dashed lines, an increase of recycling, and a slight decrease in the chemical recycling scenario for amounts available, but especially in a decrease when we include the other, or look at the other scenarios, such as when you have consumers being quite aware of recycling strategies. So once consumer behavior really changes, you have a much steeper decrease in primary plastic materials. When we look at the regional impacts, so now really looking at the environmental impacts over time, we see that for resource use, the business as usual is quite similar to the scenario that we modeled with the chemical recycling plant. But again, with the other strategies in place, you have a lot better impact. So this one really looks at resource stock, and once you run out of resources, so in 20 years, in one scenario, you run out of resources here, but you can delay that depletion when you have these 2 scenarios in place. From a resource use perspective for fossil, so this is, oh no, it's the same. Let me just think. Yeah, this is just this is not correct here, but this is looking at actually minerals and metals and not fossil resources. So just the axis description is wrong, but we have a similar trend here. For the climate change, this was the most surprising result for us, is that actually introducing the chemical recycling plant increases regional impacts over time compared to the business as usual scenario. Only when you introduce these additional strategies we can decrease the overall impact. And the reason for this is mainly because our assumptions in the model are that you have a competition between chemical recycling and mechanical recycling. Chemical recycling, we are assuming that you need mainly monomaterials still because the technology is not so advanced at the beginning and cannot deal with mixed plastics. And so it takes away a lot of the monomaterial streams from mechanical recycling. And this means that mechanical recycling is dealing with all of mixed plastics and requires quite a lot of additives. And this rebound effect basically leads to this increase in impact. Same goes with the land use category. Yeah, so to conclude, the LC results show a decrease when you look at a product level in impact for recycled plastics. But when you look at the wider system, introducing this chemical recycling capacity actually leads to an increase in impacts because it competes with mechanical recycling, resulting in this rebound effect. There are also other reasons for this. But yeah, mainly this additional requirement of virgin additives is kind of resulting in this compensation of benefits of chemical recycling. And just this shows like the importance of including the wider system, not only looking at the LCA results, but looking at the regional results, because these two results really are contradicting. And in the end, improvements are only possible with additional strategies such as technological development and raising consumer awareness. Yet, we have to say this is a study based on secondary data, and validation of the model has not yet been done. And we still aim to kind of model a few different scenarios with parameters provided from project partners. Thank you very much. It's, I mean, we're assuming that it's built in Gothenburg, Sweden, and we looked at the regional electricity mix for that. Yeah. To a certain extent, yes. And over time, you also have an increase of renewable electricity. But I would have to check. I can tell you afterwards what specific electricity mix we used. But yeah, it's the Swedish or the Gothenburg electricity consumption mix. Yeah. Any other questions? Right. Thank you.
Okay, now I can invite Stefan Kubovic from Sintef, and the presentation will be about optimizing mixed plastic feedstocks for high efficiency recycling. So please, Stefan, and thank you.
Yes, thank you. And hello, everyone. So yeah, I will share some insights from the project where we looked at optimizing this mixed plastic feedstock, because that's one which is most problematic. So yeah, while looking into this, so we know that things are improving over time, but it's still, the recycling rate is lagging behind. So there's still more waste production than actually is recycled. And especially mixed plastics are difficult to recycle. And most of it still goes to incineration or landfill. So what we tried to look at in the project was then how efficient pre-treatment could still make use of this mixed plastic fraction. And we see already that policies are changing, and that there is, at least for the plastic packaging, already recycling targets set, so that producers have to use a certain amount of recycled material in the product, and also a certain amount of the plastic waste from packaging needs to be recycled. So as Ugo already mentioned before, we looked at different waste streams, basically municipal waste, which is plastic household packaging waste, agricultural rigid plastics, which is then something like garden chairs and buckets and things like that. Rejected streams, so there are in many countries already automated sorting plants for plastic waste, mostly packaging waste. And then there are fractions sorted out which are today not fit for recycling, which is mostly mechanical recycling. We also looked at industrial waste, which is then either rejects from or waste that never came to the market, which is basically within the industry kind of waste. So there we looked then further into how can we upgrade these materials to make it fit for mechanical recycling, or also then what are criteria to diverge to chemical recycling. And then in the project, we also looked at the whole value chain from the collection, the pre-treatment, recycling, and then the product uptake, which then covers a bit what Jan was talking about. So here, just a quick overview. We had quite many different waste streams we looked at, and that's not to go through to in detail, but just to give you an idea, there was quite a bunch we looked at. And so the challenge of got mixed plastics. So one thing is that, for example, I mean, household plastic waste is a good example, because you have mixed plastic within the product, that the bottle is one type of plastic and the cap is another type of plastic. So you need to separate that before you can recycle them. In addition, you have labels on them, which are in most cases a third type of material. So again, you want to remove that. You have inks both on the labels, sometimes directly printed on the product. They need to be removed, and there might be also residues inside, which are still left from the product, that was in the packaging. So all these things somehow make it difficult to kind of go directly to recycling. So all these can be considered as contaminants, and that then reduces the quality of the material and effectively also the recycling yield. So to and another barrier we saw is that there are sorting gaps. So not every country or every region has an efficient sorting facility to actually separate different plastic fractions. That's of course an investment, so there are costs for also separate collection, and there's not always the right technology available. So in order to get the high quality recycling, you need a good collection, so either separate collection or then an efficient sorting afterwards, washing to get away the labels and residues. And then also you have to have a good understanding of your polymer composition so that you can efficiently recycle. So Ugur knows a bit more details about these technologies.
Okay. Thanks, Stefan. So in this slide, I would like to introduce you some of the equipments that we used for mechanical recycling. At VTT, on the left-hand side, you can see the Varex route, where mechanical recycling was only the option for recycling. So in this Varex equipment, we are applying an inline instrumented extrusion line for stabilizing and upgrading of the quality of recycled plastics. This means that we are melting the plastics, business as usual in mechanical recycling, and we apply filtering of the products, but then a little bit different than what industry or also in the research world is different. We apply inline rheology instrumentation, and we also monitor the spectroscopy in terms of UV vis, NIR and FTIR, and we also monitor the volatile organic compounds. So we apply smart process control, which is based on rheology controlled extrusion. So at VTT, we have developed the software to have an advanced control unit to have a smart upgrading of the plastics in advanced mechanical recycling. So this extruder is good for upgrading and homogenization of the mixed plastic waste, which is one of a kind, I would say, in Europe. And we have a lot of other different projects also that we apply this technology for at different sectors. And this is, of course, an open platform for plastics R&D and development of new material formulations. On the right-hand side, we have the Modix extruder description. This is a modular extruder based on its name also, that you can understand from its name. So we have started the here on this extruder. This during the project, this is let's say pilot scale, which is 10 to 15 kilograms per hour max capacity. And this extruder is good for compacting and homogenizing challenging feedstocks. So we kind of prepare the mixed plastic waste from whichever source you have. As you can see from here, shredded plastic pieces from different origins. It can be a foam, bulky sheet, film, textiles. It can even be a whole pillow or a textile or a shrink film, for example, from agricultural plastics waste. And you have heterogeneous mixture here, and you compact it and you make it ready as a homogeneous feed for chemical recycling. So this is the complementary approach for chemical recycling, what the terminology that we are using for describing the overall value chain. We can apply low to moderate processing temperatures here. So the intention here is not to fully melt it, but to just compact it untraditionally. And at high temperatures, not in this project, but it's also possible to dehalogenate, to remove the hazardous compounds here. And we have scaled up recently this extruder to a more close to industrial related level. And now we are working on it. You can see here that there is a conveyor belt, and this is the feeding section. So here we have a horizontal flow, and we have the vertical flow here. And yeah, I think that's pretty much it from this slide. Thank you.
Yes, thank you. So then the key insights from this feedstock preparations, as for many things, a poor input gives a poor output. Also here we saw that, okay, agricultural plastics, they are often heavily contaminated, soil and other biological residues, but it contains also a high level of or high amount of polyethylene and polypropylene, which are basically relatively easy to recycle, both mechanically and chemically. In the municipal rejects, so the ones that are today not really recyclable or considered as not recyclable, they still contain almost 50% polyethylene and polypropylene, but then often in mixed components, and also quite a high level of polyethylene terephthalate, PET, and rigid plastics, which are actually also excellently recyclable, but they are often not sorted or separately collected, but not sorted, and they contain also mostly polyolefins, so propylene and polyethylene, which are again easy in a way to recycle. So then we see that with the proper cleaning, sorting, and homogenization, plastics, even mixed plastics, can be a valuable feedstock. Sorting can be either by size, density, or by IR sensors, so you sort by type. Relatively easy also for large scale application is zinc float. So lighter plastics will float on water, for example, and heavier plastics like PET and PVC, they will sink as same as other contaminants like stones. So washing also is then removing the contaminants and labels. Quick, the results agricultural plastic. So as we said, we can homogenize materials which are otherwise kind of very difficult to handle, like foils and this kind of material. So then you will get this type of pellets, which then can be further used in recycling processes as already described. So important here was already on the farm level, things can be sorted properly, which makes then the handling afterwards easier. Municipal plastics, again, here we see a high amount in content, a high content of polyolefins, which are relatively easy to handle and recycle. Here we did some trials and see that, okay, with the proper treatment, you can get a material, a recycled material, which is close to virgin material. And yeah, so that's already the thing. So if everything is properly in place, you can get relatively high quality recycled material. Rigid plastic is so far still a missed opportunity in a way that they are just collected in a big pile, although these materials also could be recycled relatively easy because it contains a lot of polyolefins, which means polypropylene, polyethylene, and they are the perfect candidates for chemical recycling, for example. Often with this type of product is that they might be more degraded. The garden chair might have been outside in the sun for 20 years, so the plastic is not necessarily the best for mechanical recycling, but then for chemical recycling, it's just no problem. So here we had a collaboration with the university in Tampere and also Ecofellas to kind of go through such a pile and analyze and see. And then VTT did some recycling trials. So what we kind of showed is that from the collection, if there's a proper collection, and then the sorting, you can go to the feedstock preparation, either mechanical or chemical. That then goes to new products, which can then go to the market, new use phase, and by that you get the circular chain. So what can regions learn from that? So one thing, mixed waste streams can be used. Sometimes it doesn't need a lot of investment. Simple treatment methods could be enough to already increase the value of the waste. Mechanical recycling can tackle well-sorted and cleaned plastic. Chemical recycling has more ability to tolerate mixtures and contaminations. So if we combine these two methods, we can already recycle much more than we do today. Agricultural and municipal waste is often very polyolefin rich, which is also a good waste feedstock for both mechanical and chemical recycling. And the combination of these two systems is definitely better than just mechanical recycling. So combining these regions can then have like local markets and also take kind of ownership for the waste. So it's not, if there is an industry within the region that can use waste, then that is already also an incentive for the region to make sure that they collect the stuff and not just send outside. Yeah, here again, some summary of what could be done. Policies we see, we had the talks in the morning, things are changing. The EPR gets stricter. There is more design for recycling implementation, which is then helping to reduce the amount of mixed plastic. Industries are also incentivized to kind of use recycled plastics and so on. Industries, I get here kind of behind time, so try to be short. And also society raising awareness of the right storage sorting of plastic waste. And what we also heard from Jan, promoting reuse and repair, which then already reduces the amount of plastic waste that we need to deal with in the first place. So mixed plastic is not just waste, so it can be a feedstock if properly handled. So even low quality plastics can become valuable. It all depends on smart collection, the right pre-treatment, and regions can, in a way, replicate what we have done already today, because most of the things are existing technologies, just needs to be implemented in the right way. And we kind of, in our project, provide a blueprint for that. That's, yes. Yes, thank you.
Thank you very much, Stefan. We are a little bit behind the time, but we can have a 10 minutes of coffee break, and then we can come to this room again to finalize the plastics session. Okay. Oh, one question I think we have. All right. You mean the equipment-wise? Are you asking the possibility to recycle them? Okay. Yes, this is possible. Yes, we also have textiles dedicated projects, or sometimes projects have other mainstream plastics where textile feedstock waste can end up in those and contaminate those mainstream. So it is possible, and we also treat those textile feedstocks with the same equipments basically, but they just need different pretreatment stages and collection schemes. Of course, when textiles are included, there needs to be a little bit of a different dynamic, also engaging the stakeholders, the consumers, etc., reuse schemes, but it is similar. It's very analogical, I would say. Yeah. No other questions? If there's no other questions, so we can move to the coffee room. Yeah. Thank you.
Okay, let's continue then with this chemical recycling for closing the loop of plastic waste. So yeah, my name is Christian Lindfors. I'm a senior scientist at VTT. I have been working at VTT for about 18 years, quite a lot also with biomass pyrolysis, but also during the last years with this plastic pyrolysis. And Juha Lehtonen will then present the upgrading part of it.
Hello.
Okay, so let's start. So in the previous presentation, Stefan and Ugur presented this mechanical recycling. So it's always the preferred route because it requires less energy. But of course, in mechanical recycling, the plastic is grade is reduced, so it can't be used in higher grade applications. Then it can't be used for food packagings. And then, of course, mechanical recycling can't treat all kind of plastic. So if we have, for example, this multi-layer packaging, so they are difficult to treat with mechanical recycling, and therefore this chemical recycling is a better option. So here is still the value chain in chemical recycling. So first it starts with the sourcing of the feedstock, and of course the best quality feedstock should go to mechanical recycling, and then the reacts or multi-layer packaging to chemical recycling. In chemical recycling by pyrolysis, the plastic is liquefied, and here there can be different targets. So either produce the wax or liquid, or then produce some chemicals by catalytic pyrolysis. And then there is still a third step where the pyrolysis oil is upgraded. So different impurities like heteroatoms are removed, and unsaturated compounds are saturated to correspond to the steam cracker feed. So in pyrolysis, it's always dependent on the feedstock. Here the feedstocks is classified into 3 categories. So first we have this polyethylene and polypropylene. These are the most common plastic in packagings, and these are quite preferred feedstock for chemical recycling. So here target is by chemical recycling to produce wax and oils, and then further hydrotreat them so that they can be used in a steam cracker to produce olefins and used in the production of new plastics. Then we have a second type of plastic, so like polystyrene and polyamide and polymethyl methacrylate. So these are plastics which are in pyrolysis producing monomers. So for example, with polystyrene, you can get styrene in very high yield, so say over 90% styrene in your product. And then this monomer can then be used again to produce new polymers. Then on the bottom is the last category, where we have, for example, PVC. This is not good feedstock for chemical recycling because PVC is causing corrosion. So these should usually be removed from the feedstock before the chemical recycling. And of course, one challenge is that usually when we have mixed plastic, we have all type of plastic so combined. So then it's how to separate it from the pyrolysis oil and get them separate. So in this project, we have carried out chemical recycling of different feedstocks. So we have used this agricultural plastic waste, industrial plastic waste, and municipal plastic waste. And today I will present some summary of the experiments with this agricultural plastic waste. And this feedstock was received from Clean Plastic Finland. It has been already sorted by farmers, so it was quite clean. And then in the clean plastic process, some PET were still removed. So this mainly contain linear low density polyethylene, but also some small amount of other plastics. And it's then a very like good feedstock for chemical recycling. In this TREASoURcE project, we had the two targets. So first was this thermal pyrolysis to produce this steam cracker feedstock. And here target is then to optimize the liquid yield by changing the process conditions, so temperature and residence time. Here on the right side are the plots of the products. So we can say that in our fast pyrolysis process, we usually get a quite lot of heavier products. So say compounds which are solid at room temperature or like waxes, which you can see from the picture. And therefore we like optimize the condition so that we should get as much liquid as possible by changing the conditions. We can see that when we increase the temperature and residence time, liquid yield was not very much affected, wax yield decreased, and then gas yield increased by increasing the temperature. These oil products were then combined and analyzed by simulated distillation. And from simulated distillation, we can divide the product into different fractions. So we have first the heavier product, which has a boiling point about 350 degrees. So they are like wax at room temperature. Then we divided into these condensables with a boiling point between 200 and 350 degrees. And then we have the light liquid with a boiling point below 200 degrees. And then we have still the gases. And the gases were also divided in two groups. So we have the C6 hydrocarbons, which are like heavier gases and can be also condensed. And then we have the lighter gases. And by looking at this table, we can see that the optimum liquid yield was achieved at 570 degrees and 6-second residence time. So using the most severe condition here. Then our second option was also to do the catalytic pyrolysis. So here we basically, when we are using the fluidized bed reactor, we replace the sand with a catalyst. So we use the ZSM5 acidic catalyst, silica alumina ratio of 23. And here we also like varied the process conditions. We used a little bit like milder conditions, so temperature from 480 to 520 degrees and residence time from 1 to 3 seconds. And what we can say is that if we compare these results with the thermal pyrolysis, so we get less of the liquid and more of the gases with catalytic pyrolysis. But on the other hand, one interesting thing was that in this catalytic pyrolysis, using the highest temperature and longest residence time produces most amount of liquid and the lowest amount of gas. So the reason for this is that when this plastic is decomposed in the primary stage partly to olefins, so the olefins are reacted with the catalyst to be aromatized to benzene, toluene, and xylene. These products were also analyzed by simulated distillation and DCMS to detect the boiling points and also the aromatics in the oil. We can see that this boiling point curve, which look very nice, so we can see clearly the benzene, toluene, and xylene, and it has a boiling point below 225 degrees. And on the right side is the amount of benzene, toluene, and xylene, and we can say that in the oil the amount of benzene, toluene, and xylene was from 70 to 80%. So the catalyst is very selective to these aromatics, and the yield of this BTX was then below 11 to 22%, and highest yield was obtained using the most severe conditions, so 520 degrees and 3-second residence time. But Juha will now continue with the upgrading from here.
Okay, good afternoon, everybody. I'm Juha Lehtonen, research professor at VTT for the field of sustainable chemical and catalytic conversion processes, and been at VTT about 10 years now, and before that, for instance, about 15 years in the Finnish chemical and oil refining industry. But anyway, to the presentation, so our basic idea here is that we wanted to look at how to produce feedstock for the petrochemical industry, so steam crackers from the plastics also, what should be done for that before it's suitable for steam cracker feedstock, and there is a lot of unwanted compounds typically in that oil. First of all olefins, so alkenes and aromatics, which needs to be removed there or converted to other compounds, and then all kind of impurities, including chlorine, nitrogen, oxygen, and sulfur also in those oils. And the principal idea how to do that is to use the kind of the catalytic hydrotreatment there, but due to those impurities, we may need kind of also guard bed before that to remove some of the impurities before the catalytic treatment. In some previous projects, we have developed some own catalyst, and in this project we applied then that nickel palladium activated carbon catalyst developed in previous project, and then one commercial catalyst, platinum on gamma alumina as a reference catalyst then. And then we have wanted to evaluate those catalysts then under kind of standard identical kind of conditions, how it would work for the upgrading of the plastic pyrolysis oil they will deliver by polyfuels in this project. And as said, we also used kind of the guard bed there, adsorption bed before the catalyst bed, then remove some impurities before the catalytic hydrotreatment process. First of all, something about the feedstock preparation. So pyrolysis oil, which we used, was actually produced from Fredrikstad municipality, hand sorted waste plastics in Fredrikstad. I guess it's in Norway, and there you can see what all it could or can contain there. So there is polyethylene, polypropylene, PET, polystyrene, different films, plastic bags, and so on. And there you can also see kind of the average composition of that. So kind of the very, would say, complex plastic waste, also what comes to kind of the upgrading from the upgrading point of view. And that kind of the oil was obtained then from that Fredrikstad plastic waste then, and typical for the oil that produced oil was actually there was 3 different phases there, and I think there's one phase which was clearly kind of the oily phase there, and that was separated from other phases then by centrifugation there. And after that, we also then look kind of what is kind of the composition of that oil. And we discovered that there are, for instance, a lot of olefins, alkenes present there, and quite much also aromatics there. And alkenes are not something which are not very well tolerated in the steam crackers. So we need to convert principally those alkenes to alkanes and then aromatics to some cycloalkanes then there. So that would be the one target. In addition to that, there are a lot of different impurities there. For instance, 762 ppm of chlorine, which is actually pretty high content, for instance, for that catalyst, or for those catalysts used for that catalytic hydrotreatment then there. So this was more or less experimental plan. 5 runs there with those two catalysts mentioned there first. Then we also used kind of the combined strategy, used adsorbent, guard bed before the catalyst there, and then finally also we wanted to also look how it works only with that adsorbent if we don't have catalyst. And with that combined strategy with adsorbent catalyst, we had then two runs of different length there, one of 6 hours, another one of 18 hours. And there you can see all of the conditions as well then. So principally we applied the 3 different strategies. First of all, that we also have the adsorbent there, another one where we had the only catalyst there, and then kind of the combination of adsorbent and catalyst after that. And for those experiments that nickel palladium activated carbon catalyst was then applied. What comes to the result, it seemed to be that the strategy 3, where there was both the adsorbent and catalyst, is for instance best. What comes then to, for instance, the removal of olefins from the feedstock, and also it seemed to be pretty good for some removal of some impurities from the feedstock, like oxygen, nitrogen, chlorine, and sulfur there. So it seemed to be that strategy 3 was the best one there when we had the adsorbent before the catalyst there, and in that way we managed relatively efficiently to remove those heteroatoms there. On the other hand, we discovered that adsorption bed becomes full pretty rapidly. So we need to find a way how to regenerate then that bed, so remove that adsorbed components there and reuse that. Also, surprisingly, only adsorbent strategy was relatively effective for some of those impurities, so for dechlorination, deoxygenation, and the nitrification. And then on the other hand, when you only have catalyst efficient for some other components there in the feedstock. But then we had a 18 hours run. Now I have to say that 18 hours is still a very short time if we aiming for the process which we maybe could be able to run even some years there. But anyway, it gives kind of the indication whether there is some deactivation taking place in the system or something else there. And it seemed to be that at least in the figure, as you can see, that the amount of olefins started to increase during the run there, and then also amount of some impurities, for instance, nitrogen and sulfur there. So either the adsorption bed becomes full there, or catalyst starts to deactivate there, and for some compounds, deactivation, it was easier to observe them, but I would say that anyway we would need maybe more experiments, longer experiments, and experiments with only catalyst, only adsorbent to kind of better understand what it is really going on. But preliminary, I would say this was very interesting and also kind of the good result, and showing that at least in principle we can remove the impurities, convert the olefins. Aromatics are a bit more challenging, but even though we were able to convert to some extent there. So it seemed to be that putting the adsorption guard bed before the hydrotreating catalyst there is good strategy there. We managed to upgrade the plastics oil there to at least we be able to come pretty close to kind of the properties of steam cracker naphtha feedstock then. So that is something we would like to continue. Of course, we need to continue the work with investigating that impact absorption, but have the longer runs there, and then currently looking kind of the funding to continue also this work. But I would say, what comes to that it was pretty limited amount of experiment there. The results were very positive and indicating that this is kind of the prominent way to upgrade the plastic oil to steam cracker feedstock. Okay, I would say that that was maybe more or less everything I wanted to say regarding the upgrading. So thanks for your attention. Any questions? If no, so shall we continue the panel discussion, or how shall we do? So if I have understood now right, I would like to invite here now 4 panelists. There is 4 places, so everything goes very fine. So first of all, Ida Miettinen, please. Then Stefan Gubovic. And then Christian and Farah from VTT. Yeah. Hopefully have, this is bit tiny, but yeah.
Okay, this.
Okay.
Okay.
And maybe it's you were Ida in one panel already today, so tough day in that way. But let's start with some introductions anyway. Maybe you can start, please.
Yeah, thank you. So I work for Climate Leadership Coalition and I run the Circular Economy Coalition, and our aim is to make circular economy a growing and profitable business in industrial streams. Then I also chair for the Finnish Ministry of Environment as for the Circular Economy Green Deal Group, and then I work in the board of different industrial companies.
Okay, thanks. A lot of different roles. Yeah. Yeah. Okay, thank you. And then we have Farah from VTT.
My name is Farah Siddiq, and I'm working as a research scientist in VTT Research Institute of Finland. I've been working in VTT since 4 years now, and my primary focus indeed the hydrotreatment of plastic pyrolysis oil. But currently, I've been involved in this EU TREASoURcE project and also looking forward for pyrolysis activities as well.
Okay, thanks. And then another VTT Christian.
Yeah, Christian Lindfors, senior scientist at VTT, and I have been at VTT for about 18 years and I'm working with this plastic pyrolysis also for maybe 10 years.
Thanks. And then still Stefan Kupovic from Sintef.
Yeah, so my name is Stefan Kubovic. I'm working as a senior researcher there at Sintef, which is somehow similar to VTT, just in Norway. And working there in a group for plastic and composite materials, and also having several projects like TREASoURcE on recycling and circularity of plastics.
Okay, thank you. So let's start with some questions then. I think we have now had pretty good presentations already today, and maybe some of those questions we have gone through or listened to some presentations regarding those already today, but let's see how this will go. But let's start with very general questions. So as we heard, so recycling rate of plastics is still clearly below 50% in the EU. So what should be done to increase that rate then? Ida, would you like to start?
Sure, thank you. So first of all, as we heard today, it is important that we still improve the collection and sorting of different plastics, and this means also technological investments. But in addition to that, I think it's one of our main priority to create demand for recycled materials, and this means finding recycled contents and green public procurements and such, and also for the to include incineration of waste into the ETS. That's one important criteria, to mention a few. But yeah.
Thanks.
But yeah, I think it's
Please.
a combination of,
Yeah.
of all of these.
I really believe it's like that. Anybody else who would like to add something to this?
No, I would also say that it's a combination of different things. One's definitely also increasing demand, and at least what we see in Norway, it's also in certain industries like construction industry, it's very hard to introduce new materials because they have very high and very narrow standards for building materials, for example. And there it is very difficult to introduce recycled plastics. Although the industry might want to, the regulations and standards kind of block it. So their new processes have to get going to allow, in a way, the use of recycled plastics in construction industry.
Thanks. And it seemed to be that most of the recycling so far is still mechanical recycling. So there is some chemical recycling, but volumes are obviously quite small still. For instance, Neste is doing that in Finland, but the plants are not so many
But I
yet.
think also that Neste is buying the pyrolysis oil from supplier and treating it then with the purification and other treatment. So
yeah. Yeah, of course, but they are somehow in the value chain.
yeah.
There anyway. Yeah.
But I think also I don't know really the capacity of these pyrolysis plants in Finland, but still we are talking about quite big volumes which are needed to the oil refinery. So I think the plastic pyrolysis plants are still very, very small.
Yeah, and maybe one way could be there that they build kind of the bigger units there for the chemical recycling. So, but one question, of course, is that do we need some public support for kind of the scaling up and commercialize those kind of the chemical recycling solutions? Any comment from anybody, and what kind of public support is needed? Is it support for investments? Is it support still for the research, or what is needed there? Who could give an answer?
Yes, probably. Also the technology needs still some development. So that is probably needed.
Principally, it's commercial, but do you think that still kind of the more kind of the better processes are still needed there? Or
That could
what's
be,
the case there? Yeah.
May I answer?
Yeah. Please.
So I think the most important factor is that EU has been leaning only towards mechanical recycling up until for quite long. Only recently it's been acknowledged in the SUP directive to account chemical recycling as well. And that leads to the problem that we can't scale chemical recycling as we should. And without this, we're not able to reach these targets of hitting the over 50%. And I believe that's one of the most important factors, because chemical recycling, it's still more expensive than mechanical recycling, and chemical recycling needs to hit a certain level of volume to make that more attractive.
Okay, thanks. And we can't continue from that. So regarding different stakeholders then, so across the value chain, so what kind of the collaboration is needed then kind of to promote that the kind of the recycling, especially chemical recycling? What are those actors there and so on?
Probably the whole value chain should be included, so from the feedstock suppliers and then the pre-treatment and pyrolysis and then the end product development, purification and steam cracker and polymerization.
Okay, can we see this TREASoURcE project as a good example of that kind of collaboration then?
Probably we don't have all stakeholders here, so we have only some.
Yeah, but I can continue with the
Yeah, please.
Christian point of view that regarding this, including whole value chain, plastic value chain and its stakeholders, there are various projects on EU level and Business Finland project level. We are trying to include all kind of prospects from the beginning of sorting till up to the end product. At least in Europe, I can see, or at least in the Finland side, on from VTT side, we can see that we are trying our level best in inclusion of various stakeholders from starting point, like sorting, pre-treatment, then mechanical recycling, chemical recycling till the end product. But of course, on a bigger level, we do require more collaborative efforts, and policy framework should be clarified and should be realistic, in my opinion. The goals set should be realistic that we can achieve, because the chemical recycling is not now, as Christian said, is not capable enough to produce this much huge quantities of oils. So I think we should think about making more realistic goals.
Thanks. And of course, the case is so that we cannot force any stakeholder to join the projects or programs. They have to be willing to join there, and maybe with some input typically there. And that's the question there. If we move a bit more technical questions, then so looking now back, maybe TREASoURcE and other projects we have had here. So what are kind of still the main technical challenges of kind of what comes to plastic soil and produce from plastic oil, and then further kind of the steam cracker feedstock? What should be still solved there? This is more to for instance, Christian and Farah.
Yeah, maybe the challenge here is of course this feedstock. So I think currently this chemical recycling is also competing in a way with mechanical recycling. So they are using quite clean feedstock, but in future they should be able to treat more of the rejects. But of course, you can't put everything in chemical recycling, because if you have a very mixed feedstock, you will also get the very oil with very poor quality and technical challenges in your process. So, yeah.
Thanks. Anything to add to that answer? But of course, question is then also that thinking about current collection and sorting system, are they then appropriate also for kind of to promote then chemical recycling there?
I would say that this sorting technology, it's also developed all the time. So I think it's progressing all the time, and I think you can from waste you can get very well sorted the material. And then of course it's a question that what will be in future the feedstock for chemical recycling. So should it then be from then some municipal plastic waste that you can take the plastic and use it there?
Okay.
Also,
Yeah, you continue then.
okay.
Yeah.
And now what I want to say is for the sorting technology that's mostly developed now for packaging plastic, but then there's a lot of other plastic which is basically not sorted or just sorted very roughly. So there it's of course, and that can be also huge volumes like pipes and window frames and all these kind of large scale plastic items. So they're having their kind of separated collection and kind of a better sorting can also then give opportunity for these materials to be recycled.
Okay, thanks. We are soon running out of the time. First, I could maybe ask any question from the audience to the panelists. From there, one at least.
Thank you very much for this interesting discussion. I'm just reflecting on what you're saying and the presentation earlier about the life cycle assessment and system dynamics that was presented by Green Delta. They presented a different set of LCA, potential chemical recycling in Sweden, which here is different. It's in Finland, different types of feedstock, different chemical recycling. But if we want to internalize the impact, the environmental impact, let's say we solved the demand by EPR, eco-modulation, incentives, fixed the gap. We solved the technical issues of the process, we fine-tune it. But if the environmental case is still not working, how are we going to do it? Because it was very surprising for me what Green Delta presented about that projection of 50 years of chemical recycling eating up the mechanical recycling environmental footprint. How do you see that and the future step perhaps for this project? Thank you.
Who would like to start? Or do we have? Okay, anybody else who would like to answer then? Yeah.
Perhaps I can try to answer.
Okay, please.
Okay. So yes, chemical recycling currently has a lot of environmental footprint also because of basically the energy requirement that is needed for the processing and longer processing times, etc. But it's also not fully optimized process, and it also has a lot of let's say the assessment is based on a lot of assumptions also. So it's based on the assumptions that everything goes perfectly for chemical recycling. But I think even though we have shown that chemical recycling is eating mechanical recycling in some decades later on, I think mechanical recycling will still be needed as a standalone recycling technique, but they will share the feedstocks with chemical recycling because mechanical recycling is currently very limited. And there is also a technological limit to purify. Even though you have the best sorting systems, you will invent best sorting systems. Without eco-modulation and everything, it's impossible to do. Because if you imagine like a multi-layer plastics, it can have inks, glues, like a, I don't know, BOPP film, bi-axially oriented polypropylene and a PET main plastic packaging. So you cannot separate these things from each other without eco-modulation. So, but basically, what I see realistically in the industry, we will see all of these technologies, but with more eco-modulation, with less cosmetics in packaging, let's say, we might have a chance to have more monomaterial approaches. So this will also increase the share of both mechanical recycling, but chemical recycling can then use the rejects with the technological advancements and also utilization of renewables, for example, in the energy utilization.
And what comes to energy and material efficiency, typically that the first plant is always the least energy and material efficient. Second plant is better, and fifth plant is even much more better, and 10th plant is even better than that one. So in that sense, typically in LCA, we somehow look maybe that worst case sometimes also, and that is the case there.
Yes, indeed. And also, I believe the test for really large scale, let's say, virgin-based petrochemical scale for chemical recycling is not tested yet. So we don't know the real exact numbers there. So
yeah, I have also worked
approach
about 10 years in oil refining industry. So somehow kind of the believer still economy of scale. It's also very often quite efficient to do it in that way. Yeah, but maybe we can end this session in that way that if there is.
I guess Ina has one thing to say.
Sorry.
Or
yeah, please.
Cycle assessment part is that I think chemical recycling it's still in its early path, such as the electric vehicles. If anyone remembers, the batteries weren't they were far from some sustainable in the early stage, and that's what when it comes to renewable energy as well, that they were really energy intensive and using worse materials than nowadays. It needs to the development and the industrial scale to reach the certain. I think that we reached the optimal level of life cycle assessment, and it always needs to be considered as a complementary to mechanical and not replacing mechanical.
Yes, thanks. Please, any comment there?
No, I just had to comment for the mechanical recycling also, it has a limit because you cannot recycle the same material over and over again, because mechanical recycling is also kind of degrading the material over time. So after a certain number of cycles in mechanical recycling, then you can still recycle chemically. So both methods together will kind of basically work, because mechanical alone will not help. I mean, it helps for the first 5 cycles. It's an easy or kind of less energy intensive way of getting the material back into the system. But then one cannot do this unlimited times. So
yeah, that's really true. We could maybe end this panel in that way, that if you have any message still you would like to tell to the audience, so please, of course, or anything you would like to still add or comment. You don't have to say anything. We can also end the okay. If nothing, so great. Thanks to the panelists and very good discussion, and thanks to the audience for the question maybe, but anyway, and I think this is also now, I guess, end of this session. Now maybe Ugur will give us some instructions how to continue. Thank you.
Thank you very much, Juha, and all of the panelists, and also for you to being active and listening to our session. So maybe we can move on to the upstairs again, to the plenary room. We can start our meeting there at 3:15 again. So we have something like 10 minutes left. We can have our coffees and move into the main room.